Okay, we have here today another interesting integral from the UNSW Integration Bee 2020. This one was problem 11. We have the integral from 0 to 2 of the floor of x minus 2 times the floor of x over 2 dx. Okay, I think it's always interesting when we get the floor involved, and sometimes these can be pretty difficult, but I think in this one it's more to the easier side. What I'm going to do to start with is, because we have a minus sign, I can actually split this up into two integrals. And it seems like with the floor, oftentimes when we split it up into like smaller pieces, it can be easier to deal with. So let me just rewrite this as two integrals. Okay, now that we have this split up, I just want to quickly go over what exactly the floor does. Now, so the floor function, if we say we have the floor of x, like our case over here on the left, the floor of x returns the greatest integer less than or equal to x. So let's just look at a couple examples of that. If I have, say, the floor of 0.2, well, that's going to basically like round me down to 0. Or if I have the floor of 0.999, it doesn't matter how close it is to 1, it still rounds me down to 0. But if, say, we have the floor of just 1, but that goes to the greatest integer less than or equal, but 1 already is an integer, so this is just going to be 1. So using this, I think what we'll do is we'll just start and focus on this one, and I'm going to look at a graph. So before we get into the floor, let's look at the graph of x over 2. So here we have our graph of x over 2, just over the bounds of the integral, so we're just going from 0 to 2. Notice we start at 0 if you plug 0 in for x over 2, and then at 2, this thing stops at 1. But now keep in mind this is an integral, we're not interested in the endpoints, we're just interested in what's happening in between. If we want to know about the floor of x over 2, and let's just say we look at some random point in here. For this point, let's say this is like around 0.3, it's just going to take us down to 0. And if we look at some other point, like if we say, let's say we look at 1 over 2, this is going to be 0.5, but still the floor function takes us down to 0. But then even all the way over to here at like 0.999, the floor still takes us down to 0. So what's happening here for the whole bounds of the integral? The whole thing's 0. So essentially what we're doing here is we're just integrating 0, and of course that's going to be 0. So this whole piece of it's going away. So now all we have left is this piece right here. And what I'm going to do for that is I'm actually going to break that into two integrals because that's usually helpful to break it on integer values for the floor function. So I can write this as the integral from 0 to 1 of the floor of x plus the integral from 1 to 2. But then looking at this first integral, we could do another graph really quick, and I'll be kind of rough with this one because if you go from 0 to 1, the graph of x is just a line like this, right, up to 1. But what's really happening is the exact same thing we saw before. For each of these values from 0 to 1, the floor is taking us down to 0. So if we actually graph this floor of x, it's just going to be a line at 0. And so again, this floor of x in this region between 0 and 1, this is always 0. So this integral goes away, and this is just 0. So we're just left integrating the floor of x from 1 to 2. But again, because we're looking at the floor function between integer values, it's always going to round us down to the lower bound. So on these bounds from 1 to 2, this is always going to be just 1. So we're just integrating 1 from 1 to 2. We just need to integrate that and get x and evaluate it from 1 to 2. Evaluating this, we're just going to have 2 minus 1, or just 1. Okay, like I said, a pretty easy version of the floor function, but still kind of interesting. Okay, that was UNSW 2020 problem 11. Thanks everyone for watching. Have a good day.